My name is Suyan Yu. I'm a second-year PhD student at the University of Montpellier, France. Today, I'm going to talk about our recent work on analyzing crosstalk error in the NISQ year. This is a joint work with my supervisor, Ida Todrisenio. Today's quantum computers are qualified as noisy intermediate-scale quantum hardware. This kind of hardware has many three types of noises. The first one is decoherence error, which is due to the fragile nature of a qubit. It can only maintain information for a limited amount of time. The second one is operational error, including the gate error and readout error. This figure shows the error map of IBM Q Casablanca device. We can see these blocks represent the readout error of each qubit, and this is the hardware topology. We can see each line has different color which represent two different error rate. In the bottom, there are two error bars. One is H error rate and the other one is C0 error rate. The third type of error is crosstalk error. It means when multiple quantum operations are executed simultaneously, the qubit state might be violated due to the operations on other qubits. And in superconducting device, there are many two types of crosstalk. The first one is quantum crosstalk, which is due to the always-on ZZ interaction between the coupled transmon qubits. The second one is the classical crosstalk. It is caused by the incorrect control of qubits. As I mentioned before, the crosstalk can corrupt the qubit state during simultaneous quantum operations. Even though the crosstalk exists between the simultaneous single qubit operations, it is only significant on simultaneous CNOTs. Therefore, in our work, we only focus on the simultaneous CNOTs. Here, if we want to execute a CNOT gate between these two qubits independently, the error rate is about 0.8%. However, if we execute these two CNOTs simultaneously, the error rate of this CNOT gate is increased by 3 times. This huge increase is caused by the crosstalk. So now we want to characterize the crosstalk property of a quantum device, and there are many protocols doing it, and we chose the most popular one called the simultaneous randomized benchmarking because of its ability to quantify the impact of parallel instructions. Let's say if we want to characterize crosstalk between two qubits Gi and Gj, 2 steps are needed. First, you need to perform the randomized benchmarking on gates separately, and you can obtain the independent error here. And then you apply SRB on both gates simultaneously, you can obtain the correlated error here. If the correlated error is larger than the independent error, it means there's crosstalk between the two gates. So now we performed SRB experiment on IBM Q7 Casablanca device, and here is the result. This axis is C0I and this axis is C0J. This is the error magnitude. The number here represents the ratio between the correlated error to the independent error. Based on the experimental results, we found that only these two pairs have high crosstalk error. For the rest of the CNOT pairs, the crosstalk is not significant and we can just ignore them. It's important to note that SRB is only performed on CNOTs that can be executed in parallel, which means they do not share any qubits. Therefore, there is no SRB experiment on these blank spots. In order to show the crosstalk impact on the output fidelity, we performed the crosstalk injection experiment. The benchmark circuit we choose is the 3-qubit C-swap circuit shown in this figure. It can be decomposed to a sequence of single qubit gates and some CNOT gates shown in this figure. In order to inject crosstalk, we introduce two other qubits, Q3 and Q4. Here is an example when we inject two simultaneous CNOTs. We can see here we insert barriers between the two signal pairs to make them execute exactly at the same time. It's important to note that the signal pairs used for the crosstalk injection experiment are mapped to the signal pairs with high crosstalk shown in the previous slide. Here is the result. We inject different number of simultaneous signals, and the output is a distribution of different probabilities because of the noisy operations. The correct output state should be 101, which is the only output if we execute this circuit on a simulator. We increase the number of simultaneous signals from 0 to 4, and we set the 0 injection as the baseline, which has no crosstalk. According to the results, we can see the probability of obtaining the correct output is reduced as the increase of number of simultaneous signals. In the worst case, the fidelity is decreased by 33% compared to the baseline. This example shows the great impact of crosstalk on the output fidelity. So now we need to figure out how to mitigate crosstalk. There are many strategies for crosstalk mitigation from the state of the art. The first one is hardware mitigation method. For example, for Google's Sigmore chip, it uses tunable couplers for qubits to mitigate crosstalk. This is the architecture of Sigmore chip. We can see each qubit has 4 neighbors because of the tunable couplers. While for IBM chips, it uses the frequency allocation strategies to allocate distinct frequencies to the qubits. And it also reduces the number of connectivities of a qubit to avoid the frequency collision. Here is the architecture of an IBM chip. We can see the qubit has less number of neighbors compared to the Sigmore chip because it has fixed qubit and fixed couplers. However, these kind of methods are hardware-oriented. They are not general enough. On the software side, one of the most important work is the Crosstalk Adaptive Scheduler. It reschedules the simultaneous operations with high crosstalk. In our work, we evaluate the performance of this scheduler to find some insights about crosstalk mitigation. This is the framework of this scheduler. Given a quantum circuit, it first goes through the hardware mapping and routing process to make the circuit executable on the hardware. And then it is passed to this scheduler. It takes the noise data and crosstalk property into account to try to serialize some of the simultaneous operations with high crosstalk. However, the serialized operations will increase the circuit depth. It will further introduce some decoherence error. In this scheduler, it trades off between the crosstalk and decoherence error. It sets some constraints and use a cost function and put them to the SMT solver to come up with a new scheduler. Here we compare the crosstalk-aware scheduler with the parse schedule, which is the default scheduler used in Qiskit. It enables quantum operations execute in parallel to reduce the circuit depth without considering any crosstalk. And here is the table for the benchmarks. For each benchmark, we set the mapping to make sure that it includes the signal pairs with high crosstalk. We performed the experiment on this quantum device, and we choose fidelity and circuit depth as the metrics. Here's the results. Picture A shows the fidelity, and picture B shows the circuit depth result. On average, the fidelity is improved by 9%, while the circuit depth is increased by 39%. We can see even though the circuit depth is increased, the fidelity is improved as well. However, the circuit depth is increased significantly, and also the SMT solver used in this scheduler is very timely expensive. Therefore, a better method for crosstalk mitigation is needed. In conclusion, in our work, we first examined the crosstalk characterization protocol called Simultaneous Randomized Benchmarking. We performed this SRB protocol on IBM Q7 Casablanca device, and then we performed the crosstalk in. And then we performed the crosstalk injection experiment to report the crosstalk effect on the output fidelity. And finally, we evaluate the performance of the crosstalk adaptive scheduler to find some insights about crosstalk mitigation. Based on the experimental results, we found that one of the biggest problem on the simultaneous randomized benchmarking is its huge overhead. It is not scalable for large quantum devices. An alternative method to more feasibly characterize the crosstalk error is needed. And also, as I mentioned before, the crosstalk adaptive scheduler reduces the crosstalk with a great price of increasing the circuit depth, and also is also very expensive. So a better approach to trade off crosstalk and decoherence is also the interest of our future work. Finally, I would like to thank our funding agencies, the Quantum Initiative of the Region Occitanie, University of Montpellier, and IBM Montpellier. Thanks for your attention. If you have any questions, feel free to ask me.
Thank you, Siyuan. Wonderful talk.
Thanks.
If there are any questions, please add them to the chat. We have 1 minute to address them. I would ask the XTalk schedule, is that something that you implemented in as a KISS-Kit module?
No, the X, just read the XTalk. Can you see my slides?
Oh, they disappeared.
Okay, the XTalk is the crosstalk adaptive scheduler. So it is a state-of-the-art method. We evaluate the performance of this method to find its drawbacks and advantages.
Did you do the implementation, or was that implemented by someone else?
It is implemented by someone else.
Oh, okay. There was a question that just popped up. How do you parameterize crosstalk, which is used as the input for your optimizer? I think this may relate to your epsilon parameter, but I'm not sure.
Yes. So you cannot not see my slides, right? Okay.
No, they disappeared.
Okay, sorry. So
maybe you can share your slides actually again, because probably it is gone because you stopped sharing it.
Okay, so you can see it. Can you see my slides?
Ah, here they come. Yep.
Okay, so here we use the ratio between the correlated error to the independent error to quantify the crosstalk. We use this
Excellent.
ratio to quantify it.
Oh, thank you, Siyuan.
Thanks.
Very much appreciate your talk.